Yeah. For those of you that want to know what we're all about, it's like this, y'all. This is 10% luck, 20% skill, 15% concentrated power of will, 5% pleasure, 50% pain.
Hello and welcome back to a fun and exciting lesson in Algebra 2. I am Mr. Bean, and today we're talking about exponential decay functions. At first, let's remember what is an exponential function. An exponential function will always have the form where you have some initial value a, then you have your base, which is going to be your growth or decay factor, and then you're being raised to a variable. So you remember the little joke I said, if the x is not in the exponent, if you take the x out of the exponent, it's exponential, like that. See, there's no such thing as that. So it's got to be exponential. The x is in the exponent. All right, so that's what we're going to be dealing with again today, but this case it's going to be decay functions. Now reminder, here's what growth functions look like. As you move left to right, or in other words, as x values get larger, the graph will grow away from the asymptote. And in this case, we would be growing as left to right, you grow away from the asymptote, either up or down. In today's lesson, we are decaying towards the asymptote. So here's a couple graphs what they would look like. Just sketch these real quick here. Fill in the blank for the decay, and the decay would be as you move left to right, it decays towards the asymptote. In this case, the asymptote is the x-axis. In this example, the asymptote's y equals 1, but again, we are decaying towards it. So that we're coming from underneath it now this time as you move left to right, closer and closer to the asymptote. And then here's another example where the asymptote is shifted down, but again, we're starting above and shifting as you move left to right. It is approaching closer and closer. All right, so that's the visual of what decay functions, exponential decay functions will do. So here's some real-world applications. Something called half-life. When you have half-life, you'll have some type of object that is going to get smaller and smaller, and how long does it take to cut it down by half? That's called half-life. And so if you think about how that works, if you have the number 50 and you take, or let's do 100. If you take 100, you take a half of 100, that's 50. How long did that take? Then you take half of that, you get 25. Half of that, you get 12.5. And as the more halves you take, it actually never gets to 0 because you're just taking it half, 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 half. That is a decay function. So an example of that would be something like this. The aftermath of that would have radioactive material, and then you'd have this decay life of how long it takes for that to get rid of. Which, by the way, that kind of reminded me of when Mr. Sullivan kind of has some indigestion and has to pass some gas. That's what that reminded me of. Okay, don't, if you're in his class right now, don't tell him I just said that. Next, we have hot food. When you take hot food out of an oven, you ever burn your tongue on it? Maybe some hot chocolate or a hot pizza comes out of the oven. It's hot. It burns. Will it take some time for it to cool down? That's exponential decay. The temperature decays towards room temperature. We will actually do some of those in our application problems. Cool stuff. Then we have real-world applications with vehicles. The value of a car, the value actually of almost anything, will depreciate and decay over time. This is a picture of what my actual car is. This is my cool car, although I wish it was a car like this, but it's not. Yes, that's right. Crime scene investigators, CSI, they also use exponential decay. If you measure the temperature of either a body or some of the organs that are inside, you can determine at what point the body was alive because you can extrapolate back towards that. So they actually create exponential decay models to figure out and solve crimes. And then one of my favorite ones, poor Mr. Kelly. As people get older, often people, not everybody, but sometimes people, in this case maybe Mr. Kelly, their intelligence starts to decay and it goes down, and that's kind of what's happened to Mr. Kelly. I do feel bad for him. I'm sorry if he's your teacher and sometimes he's hard to understand. I know that he can just be patient with him. Okay, jumping into our meat of our lesson here. If you have our function y equals a b raised to the x, how do you know if the thing is growth or if the thing is decay? Just by looking at, without looking at the graph, if you just look at the equation itself, it's really easy. you look at the base, b. The base of the exponent, if it's larger than 1, right here, if it's larger than 1, then it is growth. If the exponential, or if the base b is in between 0 and 1, then it is decay. Now, the base cannot be negative. So that's a gimme right away. It cannot be negative. But if the base is in between 0 and 1, it's getting the whole equation is getting smaller. The values will get smaller, smaller, smaller. So that's decay. Okay, this is very important for what we're now getting into, and that is this. I just want you to either write the word growth or write the word decay underneath each of these functions, and realize that all you have to do is look at the value b, the base, to know if it's growth or decay. Pause the video now. And there are your answers. A is growth because the base here is larger than 1. Here the base is in between 0 and 1, so it's decay. Here the base is again in between 0 and 1, so it is decay. You get to completely ignore the initial value a. That has nothing to, the a value has nothing to do, whether it's positive or negative, with the growth or decay function. It's only the base. Now this one looks a little weird. It's growth. A lot of times students will get this wrong. When they see fractions, they automatically think, that's decay. It's smaller than 1. No, it's not. 4 goes into 5 more than 1 time, so this is growth. That whole number is larger than 1. This is a decay one. This is a little tricky. Many students get these last two wrong. And the reason is when you see a negative exponent, remember that that means reciprocal. So in this case, the base, b, is actually equal to 1/5 because we had to take the reciprocal because of this negative. So it's 1/5 raised to the x instead of 5 being raised. So the base of this was 1/5. That's why it's decay. And on this one, the base would have been less than 1, but because it was negative exponent, again, you take the reciprocal and make it 10/7. Therefore, that's growth. It's larger than 1. So be careful about negative exponents here. That might be something extra you write on the side of your notes just to be careful about, to star or something. That's a common mistake that we have in distinguishing between growth and decay. Here we have our first graphing for decay functions. Let's do this. Let's plug in a 0. Let's plug in the number 1 and see what we get. We're just making a quick little t-chart. So plug in a 0 here. If I plug in the 0, we get 3/4 to the 0 is 1, and then 3 times 1 is 3. So we have a coordinate point of 0, 1, 2, 3. Let's put a dot there. Do that with me on your graph, except let's make it a little prettier dot. Okay, whatever. I'm bad at this. All right, now let's do a 1. So I plug in a 1. That is 3 times 3/4. That is 9/4. What's 9/4? 9/4 is just a little bit more than 2. So I'm going to go over here 1 and go up just a little bit more than 2. Okay, now we also will have an asymptote, and the asymptote is going to follow the same rules as before. The asymptote will usually just be right here, if you can see what I'm doing, right here, right along the x-axis, unless it's shifted up or down. And since there's no plus or minus at the end of the equation, it's right here on the x-axis. So we could sketch the graph of this, but what I want to show you is this time, instead of plugging in a 2, normally we'd say, all right, in our last lesson, we plugged in a 2 to get one more value. But a 2 is going to get smaller, and sometimes it's harder fractions. So let's actually go left and figure out where up here is this graph, because it's going to be decaying down. So instead of a 2, let's go backwards and figure out what about the -1 value. So let me write this down here and follow along. 3 times 3/4 raised to the -1. What does a negative exponent do? That makes it 3 times the reciprocal. All right, so when we plug in a -1, it just means we take the reciprocal and then multiply it out. And then that would equal, 3's cancel, and we get 4. So when you plug in a -1, the y value is 4. So -1, 1, 2, 3, whoops, 1, 2, 3, 4. Okay, so that can help us a little bit. Just be careful, this is not a straight line. So when you graph it, don't just graph some straight line. It is curving up like that, and then it's curving towards, okay, that just looks horrible. It should be a nice smooth curve, and you're using the asymptote to help us out as we sketch it. So those are the three types of coordinate points. What's the domain of this thing? The domain is, again, all real numbers. Exponential graphs will always be all real numbers for domain. And then the range is everything that is above the asymptote, which in this case is 0. All right, that leads us to these coordinate points. We have 0, 1 again, or 0, comma a, just like we had before. If you plug in a 0, you're just going to get a. This is just kind of shortcuts if you need to, but you don't have to memorize these shortcuts. You can always just plug the numbers in. We'll always go through 1 comma a times b. But on decay, it's helpful on our third point, instead of plugging in a 2, it's usually a little easier if we plug in a -1 here. And then that gives you a times the reciprocal of the base. So you take the base and flip it, multiply. All right, that's everything right here is just what we did on the last example for number 1. Again, these don't have to be memorized, but if it helps you to just plug in some points, you can. Number 2, why don't you pause the video on this one and do what we did in number 1, and then I will have the answer appear here and see if you did it right. And there's your answer to number 2. Your coordinate points should have been 0, 2, 1 and 2/3, and then -1, 6. Remember, when we plug in the -1, that makes this take the reciprocal, so it would be a 3, and then 2 times 3 is 6. So that's where we get this coordinate point from. And then you just double check when you're done. Double check and say, is this a decay function? As you move left to right, it was getting smaller and approaching the asymptote. Okay, that's the idea of this. You'll approach the asymptote as you move left to right. Domain down here, all real numbers for the x values. The range, the y values are only those greater than the asymptote, which in this case is 0. So y is greater than 0. All right. Now, let's look at translations. This is the same as we've done before, so we're going to shift it h units left and right, k units up and down. Just remember you're doing the opposite of whatever that sign is there. Okay, same stuff we've been doing all year and same as the last lesson. So let's jump into this one. So let's get our coordinate points here first. I want to ignore completely what I have right there. Now, in your notes, don't cross that off. But we're just focusing on just this piece. And then after we focus on what those coordinate points would be for that, we could then shift it right 1 and up 3. All right, so 0, comma, 0, plug in a 0, the a value would be a -2. And then we'd have 1, comma, then we do a times b, which in that case, if you multiply that out, you'd get -1/2, -2 times 1/4, and simplify it. And then lastly, let's go backwards, go over here to the -1, comma, and what would we get? We would do, again, we're ignoring this piece here. We can completely ignore that. We would do -2 times the reciprocal, since the exponent's negative. So -2 times 4. -2 times 4 would be -8. All right, so what does this do? We're going to shift it. Let's see, we're going to shift it right 1 on the x values and up 3 on the y values. So now we'll have some new coordinate points. And those points are 1 and 1. And this one will be 2 and 2.5 as we add 3 to -1/2. And this becomes 0, comma, add 3, you're back to -5. Plot those points. 1, 1, 1, 2.5. And lastly, 0, -5. 0, 1, 2, 3, 4, 5. Okay, so this looks like it's growing. How is this exponential decay? Don't forget that we are supposed to graph the asymptote. 1, 2, 3. So you need to put a little dashed line on your graph. In fact, I probably should have done that first, because that's usually a good idea to do that at the very beginning of when you're sketching graphs. And then that helps us when we connect our dots what it's supposed to look like. So it's going to curve pretty sharply here and then just approach that asymptote. Ooh, that was a good one. I'm proud of myself on that one. And almost. Okay, that was pretty good. There's our exponential decay. As you move left to right, it is approaching the asymptote. The domain is all real numbers, and the range this time is y is less than the asymptote, which is 3. Okay, we're almost done with this lesson. We're on the last part here. This is growth and decay models with a % increase and a % decrease. The big thing I want to point out, and make sure you get this because this is where most students mess this up, this is not for compounding interest. Okay, those application problems that involve compounding interest, we will use a different formula. So dealing with money and its compounding interest, this is not what this is for. So please, please, please be careful with that. The way this works is when you have a model of something that is going to be increasing at a steady percentage, then we take the number 1 and we add that % increase, that rate, to the number 1. That becomes our base Right here, this whole thing is the base. Now, if it was decreasing, then we start with the number 1 and we subtract that interest rate. Really, the number 1 is the same thing as 100%. And so if it was staying the number 1, then if we had this as a number 1 raised to the t, then it would be staying the same value every time. It would just be whatever the initial value was times 1, and it would just stay the same. So as soon as we add something to this number 1, it's increasing, and as soon as we subtract something from the number 1, it would be decreasing. It would become a decay factor. So here we have these values. A is the initial value for these word problems. R is written as a decimal, so just be careful about that. And then T is your time, and time could be months, days, years, anything like that, depending on the problem. So pause now if you don't have it. Here's the next one. Here we're looking at what is the percent increase or decrease. So for this number 4 here, you're looking at the base, which is a 3. How far above the number 3 is the number 3 from the number 1? The way we do that is we take 3 and let's subtract 1 from it. 3 minus 1 is 2, so it's 2 above 1. Change it to a percent, so this is 2.00. We move the decimal twice and you get a 200% increase. I'm going to abbreviate and just say INC. It's a 200% increase. That's what this model represents, 200% increase, where the initial value was a 37. So 37 something or other, and it's increasing 200%. Okay, how about this one? The initial value was 1.08. So we had started with 1.08, and then it's decreasing. We know it's decreasing because it's below the number 1. So in this case, you take the number 1 and subtract. How far below the number 1 is this? Okay, last year when my students went through this, they really struggled, so I tried to give some different examples to help out. So I hope you're all paying attention. So we are how far below the number 1? So if we subtract that, you end up getting 0.075. And if you move the decimal twice, you'll get a 7.5%, and this is decrease. So I'll go DC. This is a decrease, 7.5% decrease. All right, next one. Again, we're focusing on the B. We know this is a percent decrease because it's below the number 1. How far below the number 1 is this? I take the number 1, I subtract 0.4. That will give you 0.6. Move the decimal twice, and you get 60% decrease. And last one, 2.7. So this is above the number 1. How far above the number 1 is it? Well, I'll take 2.7 and subtract 1 from it. 2.7 minus 1 gives you 1.7. That's how far above the number 1 it is. And then move the decimal twice, and you get 170% increase. All right, so there's our final answers on these things. I know there's not a lot of room on your notes on those, but hopefully you can squeeze that in. And we are done with the lesson. Now you're going to watch a cool little video. Oh, look at these adorable mice. That's that cute. You're going to watch some little critters in Australia. This is about a 2-minute video or so. It gives you some real interesting stuff on what happens with exponential growth of population of animals when there's no predators. I saw this several years back, and it was amazing to me. So enjoy this. This is Mr. Bean signing off. Good luck on your practice, and rock that mastery check. See you in the next lesson.
50% pain, 100% reason to remember the name.
The house mouse originated in Asia and spread with human agriculture. When conditions are right, they can quickly become plagues. In South Australia, mice outbreaks happen on average once every 10 years. They erupt after a period of wet weather creates bumper harvests. By the time they're discovered, it's usually too late. It's every farmer's living nightmare. One unfortunate farmer filmed the actual moment she realised her pest problem was out of control. Concerned for the safety of her pigs, she throws caution to the wind. Among the pens, the mice found a limitless supply of food and safety from predators. It didn't take long for their numbers to go through the roof. The secret of their success is a rampant sex life that turns breeding into a weapon. A pair of mice can have babies every 3 weeks. These in turn can breed just 5 weeks later, and their offspring 5 weeks after that. Unchecked, the numbers just keep growing. In theory, one mouse and her offspring can produce 3,000 mice a year. With few predators to control them, theory rapidly becomes fact. In one outbreak, 35 million mice were killed in just 1 month, but even this hardly dented their numbers. Eventually, stress and disease take their toll and the population crashes. For every 1,000 mice, just 2 will remain. But they are breeding machines, ready to surprise us at any time in the future.